Greetings and welcome, internet friends. Mr. Waddy here, and today we're going to learn about a whole new family of numbers that maybe you've never heard of before. Well, let's start first of all talking about the numbers we do know. The natural numbers are the numbers that are, the counting numbers, the ones that you'd started with, 1, 2, 3, 4, 5, etc. Then there are the whole numbers, and the only difference between these two is that the whole numbers include 0. Pardon me, by the way. I've got some of my kids in the background talking a little bit. The whole numbers start at 0, and those are often used by computer programmers. They usually like to start counting with 0. The integers include all of the natural numbers. They include the whole numbers, but then they also include their negative counterparts. Okay, and so they go from negative infinity to positive infinity. Hey, Waddy boys, quiet down, please. But they have no decimal values, no fractions in between. And that gets us to the rational numbers, which still include all the natural, all the whole, all the integers, but now they can include things like negative 2/3 or 7/5. And so they include all numbers that can be written as a fraction whose numerator and denominator are from the integer family. Now, one of the things I tried to throw in as a curveball here is the square root of 4 is equal to 2. And so that's a type of square root that, when simplified, could be represented as a rational number. And those are different from the irrational numbers. Things like the square root of 2 or pi or the negative square root of 3 could never be written as a fraction whose numerator and denominator are integers. These are the kinds of numbers that Pythagoras didn't believe in and may have murdered a student over the square root of 2 being shown as irrational. And all of those fit in the family of the real numbers. And so this is theoretically, unless you've already heard of some of these things before, these are all the numbers you've been doing math with for your whole life up to this point. And we are going to learn today about imaginary numbers, which very much exist and have very real-world practicality to them. So don't let their name throw you off as like, when are we ever going to use this? These numbers have very practical use. And so I've got I is the imaginary unit, and I is going to be defined as the square root of -1. And we haven't been able to determine what that square root is before because it's been peculiar to us. And so other imaginary numbers are like -4i or the square root of -3, or you can even have combinations, which these we typically refer to as kind of like the complex numbers, can have a real part and an imaginary part, and this is all a single number. And so that kind of introduces us to this little branching hierarchy of numbers. It's also sometimes presented as a Venn diagram with series of overlapping ovals. But there you go. That's the general idea. And so if I'm classifying numbers, here we go. This was an exploration. The square root of 9 is 3. And so determine which subsets of the set of complex numbers contain each number. So 3, is part of the natural, part of the whole, part of the integers. So I'm just gonna say integer. The square root of 0 is 0, and so that is included in the integers and everybody underneath it. Negative square root of 4 is this. Now notice that minus sign is not under the radical, and so that's the same as -2, which is the integers. Square root of 4/9 is the same as the square root of 4 over the square root of 9, which is 2/3. And so that can't be classified as one of those. It's a rational number. The square root of 2 is irrational, and I'd already given that example here. Other square roots would be like the square root of 7 or the cubed root of 5, any radical that cannot be reduced to right? One of the other numbers. And then the square root of -1 we are going to be calling I, and is one of the imaginary numbers. So it's from the imaginary numbers set. Imagination. There we are, there we are. Let's see, I think I can drop my inkwell there. All right, so here we go. Not all quadratic equations have real number solutions. Now, we haven't been solving all of these yet. We're actually going to look at those a little bit next unit, is my plan. However, if I asked you to solve x squared equals, let's actually even change it, -4, you could have thought, oh, I just have to root both sides, and there will be a positive and a negative for square roots. But the problem is, the square root of -4, it would have left us confused. Because if I said 2, well, 2 times 2 is not -4. If I said -2, -2 times -2 is also not -4. And so that wouldn't work out for us. And so that's been a confusing outcome. And so it has no real number solutions, because it's never going to square root. The square of any real number is never negative. So that's another way to describe it, right? 2 squared doesn't work, and -2 all squared would not work. And so since neither of those work, we actually have some numbers that we could describe. To overcome this problem, mathematicians created an expanded system of numbers using the imaginary unit I, defined as I equals the square root of -1. Notice that I squared, if I was to square both sides of this equation, I squared would equal plain old -1. The imaginary unit I can be used to rewrite the square root of any negative number. And so if r is a positive real number, okay, and I have the square root of the opposite of that, so I'm talking about the square root of a negative, I can pull that minus sign out of the radical as an I. I can pluck the I out, is what I like to say. And then by the first property, it follows that if I square this, I squared becomes the negative, the square root of r squared, the square and the square root would cancel out, and I'd get -r. And so here's our first example. The square root of -25, I could break down into the square root of 25 times the square root of -1, which is 5i. Look at that. Beautiful. Square root of -72. Let's see. Oh dear. Now I'm already getting nervous, guys. I didn't get a calculator for myself. But I could break, well, I will break out the -1. All right, so the minus sign is going to become an I. 72, what's the largest perfect square that goes into that? Well, that's 36. And it goes in twice. And so the square root of 36 is 6. The square root of -1 is I. I realize I'm rearranging this now. And the last thing I write will be the radical. And if there's any non-reduced radicals left in my answer, I always put it as the final number. So that way I don't, for instance, write this as 6 rad 2i, because sometimes your radical sign might, expand over the I, or people might misinterpret it. The I is not under that square root. Here, now, let's see. Let's just look at this part here first. So the -5's hanging out. I'd have the square root of 9 multiplied by the square root of -1. That's -5 times 3 times I, and that's -15i. All right, and so the idea is you pluck the I out. If there's a square root of a negative, you can change it to I. Let's see. Are any of these that interesting? I'm looking at 4 just because I can't think of the largest perfect square that goes into 54 off the top of my head. Let's see. Well, let's see. 9? It's 9, isn't it? So rad 9 times rad 6 times rad -1. 2 times 3 times I times rad 6. So final answer, 6i rad 6. All right, so it kind of behaves just like that. All right, complex numbers are written in standard form when it's written as a plus bi, where both the a and b are real numbers. A is called the real part because there's no I attached, and bi is called the imaginary part. Notice that if b cannot equal 0, because otherwise then 0 times I is 0, and then I would just be talking about real numbers. If a equals 0, and so then all I have is a bi, we call that a pure imaginary number. And so, right, real numbers have no imaginary part, as 0i. Imaginary numbers have b not equal to 0, so b would have been 3 or -5 or -4 or 6. And then pure imaginary numbers have the a part equal to 0. And so notice there's no constant, like here a was 2, here a was 9. In both of these cases, a was 0. All right. Now, as far as if I have a whole new family of numbers, it'd be valuable to know how these numbers can relate. And so if, for instance, two complex numbers are equal, then their corresponding a's and c's would have to be equal, and the b and the d in this instance would have to be equal. And so let's figure this out. So here's two imaginary numbers, x. Find the values of x and y that satisfy the equation. Well, I know that 2x must equal 10, right? Those are the real parts. And I know that -7i must equal, well, actually, we don't even need the I part, because we just said a moment ago that b and d must be equal. And so I'm just going to take the -7 and set that equal to y. So if I solve these now, I can just do regular algebra, and so I'd get x is equal to 5, and over here this one's technically already solved. Y equals -7. All right, I can add or subtract these kinds of numbers, and notice the only tricky part is with subtraction, that I have to imagine this minus sign being distributed to both the c and the d. And so notice that the c is subtracted and the d is subtracted. Also, as far as adding these together, it's just kind of like combining like terms, where the real parts get combined and the imaginary parts get combined, is what's going to happen. Let's just jump right in and put this to use. And so here, 8 plus 5 is 13. And if I combine -i and +4i, I'll tell you what, we'll leave that in orange. -i and 4i, combining them like terms, is just going to be 3i. I like to put a little tail on the I, so that way it doesn't end up accidentally looking like a 1 or something like that if my dot was also tiny. All right, here I'll distribute, so 7 minus 6i minus 3 plus 6i. Combine the 7 and the -3, giving me 4, and then combine -6i and +6i. Those cancel out. And so it turns out here are two complex numbers that when I subtracted them gave me a real number. There was no imaginary part left over. So that's quite interesting. Here, let's distribute that minus sign. So -2 and -7i. Plus 5i was outside the parentheses, so it did not get its negative applied to it. All right, then for 13 and -2 is 11. And then we've got -7i and plus 5i combines to be -2i. And so final answer. All right, and that's in standard form. A plus bi is the form that we write it in. So the real part and the imaginary part. Okay, Now, here's one case in which this applies in the real world. Turns out electricians, if you want to become an electrician, you have to learn about imaginary numbers. One of my friends who's an electrician had pointed out that they don't use the letter I, they use the letter J. I don't know why. But either way, they're talking about the same sorts of things. And so a lot of this language is going to be a bit of jargon to me: resistance, reactance, inductors, capacitors, all that. But here we go. Here's a particular example, and we're trying to figure out the impedance. All right, so I'm not going to have you get caught up on all the terminology, but here we got a little squiggly do called an inductor apparently, and what you do is you take that's equivalent, its impedance is equivalent to Li, and so the L would be 3, and so this is the same as 3I. Here's a zigzagger, which I guess are called resistors, and that's just the same as the real number 5. And here's well, it kind of looked like an equal sign from this angle, a capacitor, and that's the opposite of Ci, and so this is the same as negative 4I. And so if I combine these all together, I would have had 5 plus 3I minus 4I, which is the same as 5 minus I when all is said and done. So that's the total impedance of the circuit. But I don't necessarily expect you to know all those terms, but anyways, it does matter. It does matter. All right, here we go. It turns out not only can you add and subtract, but you also can multiply these things. And it kind of behaves in a very distributive sort of sense. So 4I times negative 6 is negative 24I. 4I times I is going to be plus 4I squared. Now that I squared, notice we have the fact I is the same as the square root of negative 1, we also had the fact that I squared is equal to negative 1. If I square an imaginary number, a pure imaginary number, I will get a real number out of it. And so this I squared is the same as plain old negative 1. All right. And so this would be 4 times negative 1, and 4 times negative 1 is negative 4. And let's rearrange this so it's in standard form. So that's negative 4 minus 24I. And the same thing works for double distribution. And so 9 times negative 4 is negative 36. 9 times 7I is plus 62I. Ooh, let me get that sky blue. Gotta have the sky blue. Oh, careful. Make sure this minus sign gets distributed as well. Negative 2I times negative 4 is plus 8I. And negative 2I times 7I is negative 14I squared. And so I'm already thinking I'm going to need to apply this little fact right there. So let's see. Let's combine some like terms. So I'll have negative 36, 62, and 8 combined to be 70I. And minus 14I squared is just going to become the same as plus 14. Right? If I squared is negative 1 times negative 14 is positive 14. Combine that with negative 36, and that's what? Negative 22? All right. Right? I don't know. My brain is suspicious. And so that's the way that would work. Let's see. I don't think I need to do any more of these little ones. The main trick is that I squared is equal to negative 1, and the square root of negative 1 is equal to I. And so you guys have just learned about a whole new batch of numbers, and they're completely legitimate, but they are imaginary in every way. Well, thanks for watching, Internet friends. Hope you have a great day. Bye-bye.